Good day to everyone. My name is Cristina Rotondi, and I am a postdoctoral researcher in the Department of Electronics, Information and Bioengineering of Politecnico di Milano. This work has been done in collaboration with my colleague Giacomo Verticale and with Giovanni Neglia, who is with the National Institute for Research in Computer Science and Control of Sophia Antipolis in France. So the topic of this presentation is a complexity evaluation of the optimal scheduling of the recharge of a fleet of electric vehicles in a smart grid scenario. First of all, I will introduce the concept of smart grid and of vehicle-to-grid interactions. Then I will describe you the assumption of our scheduling problem, and I will show you how to find the optimal solution of such problem by reducing it into a minimum weighted matching problem over a balanced bipartite graph. Then we will make some consideration about the complexity of the scheduling problem, and we will see some numerical results to evaluate the performance of our proposed scheduling method. Finally, we will draw some conclusions. The novel smart grid concept foresees a massive introduction of renewable energy sources in the electricity grid. Unfortunately, the production pattern of renewables, such as, for example, solar panels or wind turbines, is difficultly predictable, since it is heavily conditioned by external factors such as the weather conditions. Therefore, the smart grid is expected to face huge challenges in balancing power production and demand. In this scenario, electric vehicles are expected to play a pivotal role, since on one side they can be seen as an additional power load, but on the other side they can also be considered as a huge distributed storage bank which can absorb the surpluses in energy production due to renewables. So, one way to somehow shape the overall power load experienced by the grid is to shift the period in which the vehicles are recharged according to the energy production pattern of the renewable sources. An indirect way to do this is to change the energy price according to the energy production pattern. Higher prices will be imposed in case of power shortages, and lower prices will be imposed during periods of overproduction. However, in order to jointly manage the recharge of a wide number of electric vehicles, a new stakeholder must emerge in the energy market. Such stakeholder is called load scheduler and is responsible of managing the vehicle-to-grid interactions. The goal of the load scheduler is to define the recharge period of a fleet of vehicles in order to minimize the recharge costs experienced by the users. The scheduler receives information on the variations of the energy tariff due to the energy production of renewable sources. Moreover, since the batteries of the vehicles must be recharged by the time the users actually need to use their vehicle, the users are requested to provide information to the scheduler related to their traveling patterns. Then the scheduler must define the recharging period for each vehicle in order to minimize the recharge costs while satisfying the user requests. Now the question is, how complex it is to find such optimal schedule? In order to provide an answer to this question, we first have to specify some assumption of our scenario. We consider the case of a car rental service provider who owns a fleet of electric vehicles. We assume that the battery recharge process cannot be interrupted, so once the recharge has started, it must be completed until the battery is fully recharged. We consider a scheduling horizon of 24 hours divided in epochs of 15 minutes each. Moreover, we assume that the user's travel requests are specified at the beginning of the scheduling horizon. For the sake of easiness, each user specifies a single traveling request. We also assume that the battery of each vehicle has full charge at the beginning of the scheduling horizon, and after each travel, the battery of the vehicles must be fully recharged before being reassigned to a new user. Finally, we assume that users depart from the car rental station and come back to the rental station after concluding their car trip, exclusively at the beginning of each epoch. So here we have a pictorial view of our scenario. We see the set of users which specify to the load scheduler their departure and arrival times and the amount of energy required for the trip. This can be computed as a function of the expected covered distance during the travel. We also see the set of electric vehicles. We assume that the recharge rate of the battery of the vehicles is constant for all the vehicles. The load scheduler receives also information about the daily trend of the energy tariff. Based on all these inputs, the load scheduler must solve an optimization problem in order to define which vehicle must serve each of the users and which are the recharge periods of each electrical vehicle. The objective of the problem is the minimization of the overall recharge cost. In order to find the optimal solution of such problem, I will now show you how to reduce an instance of the scheduling problem into an instance of the minimum weighted matching problem over a balanced bipartite graph. The bipartite graph must be constructed as follows. Looking at the top left of the picture, we can see a first set of V nodes, where V is the cardinality of the set of vehicles. These nodes represent the vehicles fully charged at the beginning of the scheduling horizon, waiting for the users to come to the rental station. We have a second set of V nodes on the bottom right of the picture. These nodes represent the cars parked at the rental station at the end of the scheduling horizon. Then we have a third set of U nodes on the top right of the picture. U is the cardinality of the set of the users. In fact, these nodes represent the users departing from the car rental station after retrieving one of the available cars. Finally, on the bottom left of the picture, we see a fourth set of U nodes. Such nodes represent the users arriving at the car rental station after concluding their trip. The weights of the edges connecting each node on the left side of the picture to every node on the right side of the picture must be computed as follows. All the edges having the left vertex in one of the first V nodes on the top left of the picture have weight 0. This is due to the fact that we assume that the vehicles are fully charged at the beginning of the scheduling horizon. Therefore, they don't need to be recharged before serving the first user. Or, in case they remain parked at the car rental station for the whole day, they don't need to be recharged to be ready for the next day. Conversely, the edges having the left vertex in the set of U nodes on the bottom left of the picture may have different weights. More in detail, if the time elapsed between the arrival of the user represented by the left vertex and the departure of the user represented by the right vertex of the edge is not sufficient to allow for the complete recharge of the battery of the vehicle, then the weight of the edge is set to infinite. On the other hand, if there is sufficient time to recharge the battery of the vehicle and to assign the same vehicle to the user represented by the left vertex of the edge, then the weight of the edge is set to the minimum recharge cost, considering the trend of the energy tariff in the time window between the arrival of the user represented by the left vertex and the departure of the user represented by the right vertex. The same holds in case the right vertex of the edge belongs to the set of V nodes on the bottom right of the picture. This means that the user represented by the left vertex of the edge is the last user served by the vehicle before being parked to the car rental service. In this case, the weight of the edge is set to the minimum recharge cost computed over the time window between the arrival of the last user and the end of the scheduling horizon. Now that we know how to convert an instance of the scheduling problem into an instance of the minimum weighted matching problem, it is possible to compute the optimal solution of the scheduling problem by computing the optimal matching of minimum weight on the corresponding bipartite graph. This can be done by applying one of the many algorithms for the resolution of such problem which are known in the literature. The most famous one is the Hungarian algorithm. Once the optimal solution of the minimum weighted matching problem has been found, we can convert it in the corresponding schedule by applying a very simple conversion algorithm which works as follows. For each of the V nodes on the top left of the picture, we look at the outgoing edge which belongs to the optimal matching. If such edge has its right vertex belonging to the set of V nodes on the bottom right of the picture, this means that the vehicle has remained unused for the whole day. Therefore, it shouldn't be assigned to any user, nor it has to be recharged. Conversely, if the right vertex of the edge belongs to the set of V nodes on the top right of the picture, then the user represented by the right vertex has to be associated to the vehicle represented by the left vertex. Then we jump to the nodes belonging to the set on the bottom left of the picture, representing the arrival of the user after the end of its trip. And we look again at its outgoing edge belonging to the optimal matching of minimum weight. If the right vertex of the new edge is still in the set of U nodes on the top right of the screen, then it means that vehicle will be associated to such user after the return of the first one. However, before being assigned to a new user, the vehicle must be recharged. The beginning of the recharge is scheduled for the epoch which guarantees a recharge cost equal to the weight of the considered edge. These steps are repeated until we reach one of the V nodes on the bottom right of the graph. In order to better understand how the optimal solution of the scheduling problem can be computed, I represented a very simple example in the picture where we can see a scenario with 2 users and 2 vehicles. So we have 4 nodes on the left side and 4 nodes on the right side of the graph. The edges belonging to the optimal solution are highlighted in yellow. Since the complexity of converting the scheduling problem into an instance of the minimum weighted matching problem, finding the optimal solution of the minimum weighted matching problem, and mapping it back into the optimal solution of the scheduling problem has polynomial complexity, it is possible to prove that the scheduling problem is polynomially reducible to a minimum weighted matching problem. The reverse process is also possible. In the paper you can find details about the proof to polynomially reduce the minimum weighted matching problem to the scheduling problem. This can be done applying a classical Cook reduction approach. It follows that the scheduling problem and the minimum weighted matching problem are computationally equivalent. Based on these results, we can compute complexity upper and lower bounds for the scheduling problem. Let's now move to the performance assessment of our proposed scheduling algorithm. We compared the daily recharge cost achieved with our approach to a benchmark scheduling method which simply recharges each vehicle directly after the arrival at the recharge station. We considered a fleet of various sizes ranging between 200 and 500 vehicles and 500 requests per day. As you can see from the table, the recharge costs obtained with the benchmark approach are on average 17 to 25% higher than the recharge costs obtained with the optimal scheduling approach. This is due to the fact that the optimal schedule is much more effective in locating most of the recharges during the periods in which the energy cost is lower, as you can see in the graph at the bottom of the page. So, coming to the conclusions, this work evaluates the computational complexity of an algorithm for the optimal day-ahead scheduling of the battery recharge of a fleet of electric vehicles. We also provided polynomial complexity upper and lower bounds and evaluated the performance of our proposed scheduling approach with respect to an immediate recharge method, showing that considerable cost savings are achievable. Thank you a lot for your attention.